Ladies and gentlemen, may I have your attention, please? Thank you. Ladies and gentlemen, dear colleagues, dear esteemed guests, it is my pleasure to welcome you to today's Young Academy Distinguished Lecture, the second within our Young Academy Distinguished Lecture Series. And I have to say, I'm really excited to see so many of you here. I mean, who would have thought that a dry and abstract topic like math and infinity would draw so many people here? So many, actually, that we had to move the event from Sitzungssaal to Festsaal. So, well, thanks for coming. Perhaps it's suitable to quickly introduce ourselves, because you're so many people, I can't assume that everybody knows who the Young Academy is. Well, actually, the name tells you, right? So we are the young edition of the Austrian Academy of Science. And the Young Academy Distinguished Lecture Series is our own lecture series, Nomen est Omen. Well, I'm emphasizing own here because for most of its existence, the Young Academy did not have their own lecture series. Very much in contrast to the Austrian Academy of Science, which actually runs so many lectures or lecture series that sometimes they ask us for help to suggest topics and speakers and so on, right? So on one day when we were discussing what to suggest to the I shouldn't say this. So the Austrian Academy of Sciences, it just occurred to me that really we should have our own lecture series, right? And this was how the Young Academy Distinguished Lecture Series was born, and fortunately also the Austrian Academy of Science was happy with this, and that's why we can meet today in this format. So the idea of the Young Academy Distinguished Lecture Series is to bring cutting-edge scientific topics to the public, presented by an invited distinguished expert and a member of the Young Academy in an interactive and accessible format. And distinguished is indeed the key here. For each distinguished lecture, we invite one of the world's leading experts in a scientific field of public interest. And I'm proud to say that after an excellent start with the first Young Academy Distinguished Lecture in January this year, we have once again succeeded in meeting the ambitious goals that we set ourselves. Thanks to the efforts of today's lecture's host, Professor Sandra Müller, where is she? Including the young mathematician, the youngest present today, and Professor Michael Eichmeier. Both are professors at the University of Vienna and my colleagues in the Young Academy. So thanks, Sandra and Michael, for having made possible this exciting event today. Now, the format of the Young Academy Distinguished Lecture Series actually only provides, or that was the idea, for one distinguished speaker per lecture. But Sandra, following a suggestion by Michael, has managed to persuade us that we should have two distinguished speakers this time, given the special occasion. So I would like to extend a warm welcome to Jan von Plato and Hugh Woodin. We are very honored to have you as our distinguished speakers today. Now, the special occasion that we are celebrating today is the 100th anniversary of Kurt Gödel's enrollment at the University of Vienna. We all owe thanks to Michael Eichmeier for having alerted us to this fact. Gödel is world famous for his incompleteness theorems, and I dare to speculate that he might not have formulated them had he not started his intellectual journey in Vienna. I'm not sure, we will see whether you agree with this, but that's my speculation. Okay, why? Well, if I were to say Vienna is just such an inspiring place to be and has been so already 100 years ago, well, probably nobody would protest. However, there is a specific reason. And this is the fact that Gödel very early on got involved in a discussion group later known as the Vienna Circle. The Vienna Circle consisted of philosophers and scientists whose agenda was to make philosophy scientific with the help of modern logic. On the basis of the assumption that there is knowledge only from experience, philosophical statements were logically analyzed in order to find out if they could be reduced to simpler statements about what is empirically given. So philosophical statements, thus reducible, they were regarded as scientifically acceptable, and all other philosophical statements, in particular those of metaphysics, were dismissed as unscientific and meaningless. The logical positivism of Vienna Circle is potentially life-threatening to philosophers like me, who specialize in metaphysics. Therefore, I find it all the more remarkable that Gödel, who was deeply influenced by the group's appreciation of formal logic and their preoccupation with the foundations of mathematics, yet remained aloof from their philosophical views and indeed ended up using logical tools to save metaphysics, namely as the ground on which mathematics stands. Well, if you think this is too bold a diagnosis, we might at least agree that Gödel's incompleteness theorems imply the following. There are true statements in mathematics which cannot be proved mathematically, but which, contrary to the spirit of logical positivism and formalism, are nevertheless not meaningless. Rather, these statements point to the existence of a different kind of knowledge about a different kind of reality. Perhaps one does not even have to be a Platonist like Gödel, that is, one need not believe in a sphere of logical mathematical concepts as a separate realm of being, to find the idea of an extended notion of knowledge and reality intriguing and worth considering. And at this point, I really should hand over to somebody who knows Gödel's work by heart. Our first speaker, Professor Jan van Plato of the University of Helsinki, is an expert in probability theory and proof theory, and the author of key publications in both fields. In particular, I would like to mention two monographs, Creating Modern Probability and Structural Proof Theory, both published by Cambridge University Press in 1994 and 2001. More recently, Professor van Plato has turned to the historical aspects of his fields, including studying Gödel's notebooks on logic and the foundations of mathematics. Professor van Plato is one of only a handful of scholars able to read the shorthand in which Gödel's notebooks are written, and he will now share with us some of the results of his exciting research, which was supported by an advance grant from the European Research Council. Please come to here. Yeah, it's fine. Yeah,
30 minutes.
It's 30 minutes. And we will have all the lectures one after the other, and then a final Q&A in the last half an hour. Yeah. So the floor is yours.
Yes, thank you. Now I'm looking for the pointer. Can someone give me the pointer? So, thank you very much. I was supposed to speak in German, auf Deutsch, that I learned as a child, for logicians, but then I understood that this was actually not the case. It's impossible that all of you would have a formal education in logic, though I think, but that's another thing. Let's put it that way. So I will try to cater something for everyone. This work I'm telling you about has been done in this ERC project that was mentioned. And now Gödel, he was very peculiar in that he thought that if a thing stands on a piece of paper, it is somehow much more real than if it's just being said. So this then implies that you cannot throw away anything on which anything is written. So he had his brother Rudolf send the all his papers to Princeton when he had moved there in 1940. Maybe that was after the war. But literally, school notebooks, just receipts and all sorts of things. Now, these have not been studied before. Well, 2 pieces of Gödel have been recovered in the 80s from his shorthand, but now we started with this project in 18. And just to show you, when I say all things written are there, so this is 6-year-old Gödel writing perhaps the 0th Gödel theorem, 1 + 1 is 2. Then when he was 9, he had to learn the Sütterlin-Schrift. I guess you all know what it is. I can read it from here. Ich turne, ich turnte, ich hatte geturnt, ich habe geturnt, ich lese, and so on. Actually, the Deutsche Schule Helsinki taught me this thing when I was 10 years old. I had forgotten that I'm able to read it, but it sort of came back. Then when he was writing Latin, like here, a piece from Ovid, then he would use a nice cursive handwriting. And when he just wrote for his own fun, then he would write like this. I was able to determine that this piece of text is written in 1940, so he had just been in Princeton since March 40. And he was training his Italian by copying articles of interest from newspapers. This one, as I happen to know Italian. Un noto aviatore americano ucciso durante una notte d'amore. So a well-known American aviator was killed during a love night. And then there's the story, but we don't have time to go into details. But anyway, writing things and in 4 different forms. So the Sütterlin, the cursive Latin, and then this sort of free writing, and then the shorthand. So 4 styles of writing. So that was something very central to his whole being. Now, I'm telling you things from the book that I published this year earlier, and it's not just a virtual book, but thanks to Professor Friedrich Stadler, in whose series the book is published, I can prove you the actual physical existence of this book, Portrait of Young Gödel. Right. So things come from there mainly. This is his last school year, the spring of 24, and he is now writing an essay. I'm sorry that I don't have time to translate it into English, and I have to even, since I don't see so well, Hausarbeit, it says. Now, he's very unsure about it. The cancelled thing is, die menschliche Seele besitzt 3 Fähigkeiten. No, not good, cancelled. Die menschliche Seele kann in 3 verschiedene, not good. Die Tätigkeit der menschlichen Seele ist eine dreifache. Mittels der Vernunft sucht sie, alles zu begreifen. Mittels des Gefühls alles auf sich wirken zu lassen und zu genießen. Und mittels des nach außen gerichteten Willens alles zu beherrschen. Ja. And then it goes on, and then his sort of philosophical credo is already there. He thought that philosophy is the sort of the crown of our culture. And there must be a philosophy that is not materialistic because it has no place for the ich, for the person, the thinking person, or however you want to put it. And it must not be purely spiritualistic. Then he says he's convinced that there's such an absolute philosophy. And I think I can say that all of his life he was searching for this absolute philosophy. He didn't find it, but I think he made good steps ahead in this project that he saw as something that had begun in classical antiquity. Now, there's a place where he was reading Grillparzer, which is the national poet of your country. I think he may have thought about these. Now, he was drawing the great line of development of science and philosophy from antiquity, but then he also thought that this is nothing compared to where we can arrive. And then this was 6 years after the First World War, so he was very sort of strongly pacifistic in this essay of his. I didn't read all of Grillparzer, but I just found them from the internet. So this is a bit further in the notebook. I didn't know that the spider's net is a spiral, but if you think about it, then that's the only reasonable way for a spider to do it. Not like concentric circles, but a spiral. And there's Sütterlin-Schrift, Ordnungsskorpionen, I think it says. And then comes the steam engine and so on. And then comes another notebook. You have there Mittelschule, Redeübung, Molekulartheorie. And then there's this, let's see if I am able to use this one. Oh yeah, you see, that's Gabelsberger, it says Frühjahr. So it's typical of Gödel to mix longhand and shorthand, and even English words. And this one has, he had a very, very profound understanding of statistical mechanics. And now that was the theory that matter consists of atoms. That was championed, that was sort of fought against by Ernst Mach of this university very vehemently. Now, Gödel then said that there's a view of scientific theories in which you think that it's just a way of representing observable phenomena. But that's not good, because he says that the limit between that which is immediately observable and that which is theoretical construction is nowhere fixed. And then he even has the courage to mock Goethe in his school Redeübung. As you see, Goethe said that the telescope and microscope muddle sound human understanding. So I think this may have been a courageous move in the Real Gymnasium in Brünn, where he was studying. So he was in Brünn until 24. Now it's Brno. I never knew how you say B-R-N-O, but then one Czech person said Brno, so okay. So I showed you a bit already some signs of his scientific and philosophical orientation. He studied physics first, then he changed for mathematics. A bit strange because quantum mechanics had just been invented, so why would you do the less exciting thing? Then he, as was mentioned, started, sorry, that's my view. I am a logician, but why didn't I start quantum mechanics? Anyways, now then these are now completely new discoveries that he had been following Rudolf Carnap's Axiomatikübungen from May 28 on. Carnap was a Privatdozent here. So 1 year earlier, Gödel's friends Herbert Feigl, later a well-known philosopher in America, and Marcel Natkin, who became a photographer and a writer on that topic in Paris, they attended, Gödel not, but then the next year Gödel attended. And Carnap's diaries that Viennese colleagues are publishing now, they contain mentionings of Gödel. So what are these exercises? They can be found in the little book Carnap was writing at the time, which came out in 29. It's called Abriss der Logistik, like outline of symbolic logic would be my translation. This second part of this book is about applied symbolic logic. You have axiom systems for set theory, natural numbers, axiom system for topology, neighborhood axioms, projective geometry, and so on. And then you have here last, you have this anhang, so supplement, you have exercises. And Gödel was solving these Carnapian exercises. He was formalizing what you call second-order arithmetic, and he formalized proofs. So a formal proof is something in which all the mathematical statements are written in a symbolic language. And then each step in the proof is just taken from a pre-existent set of rules of proof. So then you can check the correctness of every line, if it's a correctly written formula, and you can check that the step follows the rule. Actually, this checking can be done by a computer, that's why you call it formal. Secondly, he formalized Frenkel's set theory from the 10 Vorlesungen über Mengenlehre from 27. And then this was a philosophical thing he did. And then he formalized point-set topology from Hausdorff's book, Grundzüge der Mengenlehre. So I can see it from the notation. The notation reveals the source of Gödel's things, but also partly Carnap's suggestions. Also Hilbert's geometry, that was one of the exercises. Now, In 2019 in Princeton, I was visiting the Gödel collection. So I might remind you that the Gödel papers, they are available on 35 microfilm reels. One reel has about 1,000 pictures, and one picture is 1 to 2 pages. So you get shorthand pages in maybe 20,000 or 30,000, I haven't counted, but very many. And so there was this notebook called School Logic Notebook, and when you open it, then it says Übungsheft Log, so it's written there. But then when you look at this notation here, then if you have training in logic, you see, well, this can't be a school notebook because this comes from a book that was published in 1928, namely this book, Grundzüge der theoretischen Logik. And this was absolutely decisive for Gödel. Carnap had read it in May 28, as his diaries tell, and Gödel must have then studied it in the following autumn. So I show you, now it becomes a bit heavy for those who are not logicians, but bear with me. Here Gödel defines, so the x and y you can think of as natural numbers, and the alpha 1 and so on, that's a property of natural numbers. And erb alpha 1, it says that a property of natural numbers is hereditary if and only if for all numbers, if x has the property, if y is the sum of x and 1, so the successor of y, then y also has the property. That's the standard definition. And then an x is a natural number. That means that for all properties of natural numbers, if they are hereditary, and if one has it, then x has it. So that's how you have arithmetic induction inbuilt. I don't know where Gödel took this from, probably from his head, since I haven't seen them written down in this form anywhere. Now, the first thing he proves is that 1 is a natural number. So you put, in place of x, you put number 1, and then you get, this is what you have to establish. Now, it's very easy because you see, this thing is assumed here and it's claimed here, so that comes. But now, next, he does something that is nowadays described as Fitch-style natural deduction. And this was like 20 years before Fitch, or maybe 30. So he assumes, so that's for outset. He assumes that A is a natural number and B is A plus 1. Then he assumes that P1 is a hereditary property and 1 has it, and then he goes a long way and shows that B also has this property. And then he closes the assumption, introduces this implication here, and at the same time he quantifies over the eigenvariable that you have here for the hereditary property, that one. And then he even generalizes here for all x and y. And then you at once guess, if you're a logician, but the next step is, it is to show that if A is a natural number and B is a natural number and C is the sum of A and B, then C is a natural number. So that's maybe on the next page. No, it's not. But now I just want to show you how complicated it becomes. And these are, I think, by far the most complicated formal proofs ever done until 1928 in mathematics. So the proof begins here. There's this assumption, and there has been doing some changes there. Then it goes on, and it goes on, and it goes on, and it goes on. Here you see there are at least 5 nested assumptions, and all of it is done impeccably. Never does he tell what the rules of the system are. He just didn't stop to think about it, but he just did it. So Gemeinsam was perhaps the better logician because 5 years later he invented the same thing, but he wrote down a set of rules of inference. Anyways, so this was, I think, an extraordinary achievement, but then he just put it aside. So this was actually still the continuation of this. I printed once this and I taped it. It was about this high. So that's the proof. Then there are remarks in the Carnap diaries which show that Gödel was moving towards solving his first big problem, which was to prove what you call the completeness of quantificational logic. Now, in mathematics, you can say for all x, there exists a y. let's say x and y are numbers. Then you can say, for all x, there is a y such that y is greater than x, and y is a prime number. So now, with the help of these quantifiers, for all and there exists, you have expressed that there's an infinity of prime numbers. But you can express much more complicated things, like for all x, there's a y such that for all z, which you encounter when you go to function theory. And now, the task was to show that the simple rules that govern mathematical proofs with these quantifiers, that they actually are sufficient, that nothing is left unprovable that should be provable. So we say that he proved the completeness of quantificational logic. So he had already thought about it in December. This Entscheidungsdefinitheit is a concept that refers to that. So this problem is listed in Hilbert and Ackermann, and it took Gödel 6 weeks to solve it. This is the unserem doctoral thesis. It's 50 pages. It's quite straightforward. You find it in English translation here. I don't publish anything in German because my Kinderdeutsch is not grammatical, and I would need an assistant to fix the ends in the end of the German words now. Anyway, so it says Einleitung and so on. So this is like straightforward. But there's something funny here. Even if you don't read shorthand, you can see that this 1 and 2 are upside down. So one of Gödel's habits was to start notebooks from both ends. And then, of course, at some point they hit each other. And hopefully at least one of the stories is finished by then. Actually here you have a sketch of the proof of the independence of the principles of quantificational logic, which he didn't discuss in his published thesis. Anyway, then he was Dr. Kurt Gödel, as you can see that he's quite set at being Dr. Kurt Gödel. So I think I'm doing pretty well. Now we have already completely cleared. Then this is a remark from Carnap's diaries that the inexhaustibility of mathematics, see separate page. He has come to these thoughts on the basis of Brouwer's talk in Vienna, namely that mathematics is not formalizable without residue, and he seems to be right. Now, I was 2 years ago in Princeton again looking at the originals of the Gödel papers, and there's also the correspondence and so on. And I found in the Carnap correspondence then this separate page that Carnap obviously had typewritten on the basis of his discussions with Gödel. And you have very, very clearly some of the central ideas. First, he says that Brouwer made him to think that mathematics is inexhaustible, that you have to always create from the fount of intuition. Yeah. But then here this is now for logicians. He says, well, let's just consider one-place arithmetic predicates, and let's just diagonalize their sequence if you put them in lexicographical order. Now, this is the central methodology of the incompleteness result. Now, I think I just, yeah, more or less. Can I, let's see. Oh yes, it works here also. Lexicographically ordered expressions for sequences. Counting expression is first-order formula. That's old-fashioned, like Zählaussage in one variable. Then you diagonalize it. So now this is one of the two main sources of incompleteness, and you don't see much. Can anyone read anything except unrein, so undecidability sketch? And by the way, on the left you have this. Usually you don't use ink for shorthand because the thickness of the line is crucial. You use a pencil, special pencil. But sometimes he just wrote it like that, whatever happened to be at hand. Now I was able to read this thing here, I had this notebook, and then light was coming just like here. And then I found the right angle, and I found that the pencil had left indentations in the paper. So I was able to actually decipher this thing. At least I think so. Somebody may try to fault me that I didn't read right, but what I read makes sense at least. Now, this is then the second incompleteness, main incompleteness notebook. It says, Arb unrein. Now, I will just, for fun, read a bit. It's a bit weak, but it says, Die Entwicklung der Mathematik in der Richtung zu größerer Exaktheit hat bekanntlich dazu geführt, weite Gebiete von ihr, it's cancelled, der Intention nach die ganze Mathematik zu formalisieren, in der Art, dass das Beweisen nach einigen wenigen mechanischen Regeln vollzogen werden kann. So, that's the famous opening passage of the incompleteness paper. I don't have to translate to you because you can just check it from the English translation of the paper. And if someone else doesn't read German. So, now, the notebooks about incompleteness, they revealed something quite dramatic. Namely, Gödel first had a completely different semantic approach to incompleteness. He wanted to give a truth definition for Principia Mathematica, that is the higher order logic, basically. A set theoretic truth definition. And then he wanted to prove a meta theorem, which you see here. It says, well, I'll translate now. One convinces oneself easily by complete induction of the correctness of the theorem. Each provable formula is true. And then he even says, allerdings kann dieser Satz nur mit Hilfe des Auswahlaxioms bewiesen werden. So this can be proved only by the help of the axiom of choice. Then he met Johann von Neumann in September 1930, and he was explaining his completeness result. Then he said, well, you would expect that the next thing is to prove the completeness of higher order logic, but nothing of the kind is true. And von Neumann got very alerted and wanted explanations. And then they also met in Berlin afterwards. And the result was that this truth definition completely disappeared from the paper. And von Neumann had suggested that Gödel should do all of the work within number theory and primitive recursive definitions of things. And that then in the end, you don't even find the word true in the paper. Well, maybe some, but not in any technical sense. And the only semantic component now is that some primitive recursive, so things, the correctness of which you can decide by a computer, so those are assumed. That's the only semantical component. So he rewrote the whole paper from September to November in about 2 months, following this suggestion by von Neumann. Well, I think I just told you all of these things. Well, one thing is that the famous Gödel numbering. So in one notebook from the summer of 1930, so there is Gödel numbering, but then it's crossed over. And then later he took it. So he had been thinking about this, it seems, well before von Neumann. So that was quite, then there was another quite dramatic story about the second incompleteness theorem, but I will not go to it here. This is now the finished paper. It reads just as I read to you. Die Entwicklung der Mathematik, maybe some little change, but anyway. And then you see this part 1 here, but well, maybe I just give a little hint to you. You don't see any part 1 here. So something pretty strange happened. And what it was, you can find out from this book. That was the first Gödel book I did. This was published in 2020. The title is a talk of Gödel's he gave somewhere in the east coast of US when he was in Princeton from 33 to 34. So it was believed to be lost, but we found some pages in one place, and in another reel, 10 reels ahead, we found some other pages, and we were able to put them together. And that made for this whole talk. This is quite a nice talk because he is very explicit about some things of which he doesn't say anything elsewhere about incompleteness. So it has all these different notebooks. Well, they may be a bit esoteric, but it has also about 6 lectures on incompleteness that anyone can read. Some of them quite long, about 20 pages in print. So lectures on incompleteness had given in Hans Hahn's seminar on logic, which would lead me to the next topic, but I will just use one or 2 minutes, and then I'm finished. Namely, Gödel was by now then with this result world famous, and of course Hans Hahn was very proud about his brilliant student, and then put up a seminar on mathematical logic 31 to 32, and this is now the Gödel book that will come out next year in Stadler's Vienna Circle Publications series under Gödel's and Hahn's name. So there's a set of notes, actually typewritten, but you would have a great difficulty reading it. The original in Princeton is readable. It has about 22 seminar gatherings, and 1/3 of them were Gödel presenting his results. So we have yet another version of each of his great early results. But also much more because he had been starting to work with intuitionistic logic, and in this seminar he was talking about those results. And then we also had an enormous luck that we found Gödel's trial lecture for becoming a docent that he gave in February 33, which is about intuitionistic logic. It's in this coming book. It's about 14 pages long, whereas his publications about those results, they were each 1 page long and just stated the result and didn't tell how he came to it and how to prove it. So all of those are now covered there. Now, this is maybe 20% of what there is to do about Gödel, maybe more than 20, maybe half of logic and foundations. If you count set theory separated, there will be over 1,000 pages of things about set theory. If you start looking at his physics things, there will be thousands of pages about physics nobody ever looked at. If you're interested in Leibniz, there's 1,800 pages about Leibniz nobody ever looked at, and so on. So maybe I just stop here. Thank you.
Thank you very much for this really exciting insight that we got into the working process of Gödel. And we'll now come to the more mathematical contributions of this evening. Gödel's incomplete theorems were purely theoretical. Today, however, we know many examples from mathematical practice, and one of the most notorious is the study of large infinities. Our next speaker, Professor Hugh Woodin, will introduce us to this fascinating subject, making a strong case for the existence of mathematical truth beyond proof. Professor Woodin is based at Harvard University, and he is the first person ever in Harvard's history to be a professor of both philosophy and mathematics. And he's a world-leading set theorist who made pioneering contributions to the study of large infinities. For lay people like me, his fame is visibly marked by the fact that there's a mathematical entity named after him, the Woodin cardinals, and I'm sure he will be able to explain if you ask him what this is. So it's a type of very large cardinal numbers, that's what I read. Woodin has been awarded the Karp Prize of the Association for Symbolic Logic and the Hausdorff Medal of the European Set Theory Society, and he is a member of the American Academy of Arts and Sciences and the National Academy of Sciences in the States. Professor Woodin, we are looking forward to your talk. The floor is yours.
So I will apologize in advance once I figure out how to use the pointer. Oops. Okay. top. So how does it know where I'm pointing? Okay, necessity of truth beyond proof. So I should, whoops, I'm having some technical difficulties already. This is going to be a technical talk, but I've organized it into parts. So when I start a new part, you can forget about the previous part. And it's like a restart, okay? So, part one. So the limits of proof, as we just saw, they're the Gödel incompleteness theorems. If mathematics is free from contradiction, there are propositions which cannot be deduced from the axioms. Even more seriously, if mathematics is free from contradiction, mathematics cannot prove that mathematics is free from contradiction. But do we have to be worried about this? Are there like real problems here? So I'm going to show you a different proof of the incompleteness theorems, which show you that is, you can't dismiss them. Okay, so I have to remind you or introduce you to Turing machines. So this is an idealized, very simple computer. There's an infinite tape. This isn't terribly realistic. Partitioned into squares. Each square contains a 0 or a 1. There's a scanning head which is positioned on some square. The Turing machine has a finite number of active states and then one additional halting state. And the program of the machine specifies action based on situation. It's a very simple model. Okay, so what's the situation of an active Turing machine? Well, there's the symbol in the scanned square. Two possibilities, 0 or 1. Then there's the active state of the Turing machine. Well, states S1 up to Sn for an n-state machine. What are the possible actions? Well, we combine them into 3 steps. Step 1, the scanning head writes 0 or 1 in the scanned square. Step 2, the scanning head moves 1 square to the left or right. And then step 3, the Turing machine enters a specified active state, or it enters the halting state and then is no longer active. So here's the head, there's the square, write 0 or 1, move left or move right, and enter another state. There are 2n many possible active situations for an n-state machine. There are 4 times n plus 1 many possible actions. So a program specifies for every active situation an action. So there are 4n plus 4 to the 2n possible programs for a Turing machine with n active states. Okay, so this is the Berry paradox. Pick a number bigger than 0. We'll say that it's n simple if there's a Turing machine with n active states and a program P. And when you start that program on a tape with 0 in every square, the machine eventually halts. And when the machine halts, the symbol 1 is written in exactly k many adjacent squares, and the scanning head is positioned at the leftmost square containing the symbol 1. Okay? Well, we just counted up how many possible n-state Turing machines there are, so there are at most 4n plus 4 to the 2n many n simple numbers. The limits of proof. Well, 1 is 1 simple, that's easy. 2 is 2 simple, and 2 is the only 2 simple number besides 1. All right, let's take a larger n. How about 10 billion? Consider the statements. 1 is not 10 to the 10 simple. 2 is not 10 to the 10 simple, ... We have an infinite number of very explicit statements. All but 4n plus 4 to the 2n of these statements can be true. And that's bounded by, I chose 10 to the 10 to the 100th, which is a googolplex. So I wrote down an infinite number of statements. Well, I didn't write them all down. And at most, a googolplex of these statements are true. A finitist has to accept that statement. There's no esoteric mathematics here. Well, if mathematics is free from contradiction, then mathematics cannot prove a single one of these statements. Not one. This is for any system of mathematics ever written down on Earth by humans. If you increase n to a googolplex, this is for any system of mathematics which is expressible in our physical universe. You also get the second incompleteness theorem. Let's take a number less than a googolplex. Suppose mathematics proves there are at most k many 10 to the 10 simple numbers, and that there happen to be k many 10 to the 10 simple numbers. Then mathematics is inconsistent. This is for any system of mathematics ever written down. So you now get the second incompleteness theorem. If mathematics is free from contradiction, mathematics cannot prove that mathematics is free from contradiction. Why? You just start with k equal to a googolplex. If mathematics prove mathematics is consistent by what I claimed, there can't be a googolplex many and 10 to the 10 simple numbers. Subtract 1. Repeat the argument. After a very long time, but less than a googolplex many steps, you have a contradiction. So mathematics cannot prove that mathematics is free from contradiction. V is the ultimate mathematical universe. It's the universe of sets. It's the ultimate mathematical conception. I'm biased as a set theorist. The conception is sharpened by the formal ZFC axioms. One cannot use the ZFC axioms to prove any of the statements that k is not 10 to the 10 simple, unless the ZFC axioms yield a contradiction. Maybe this is evidence we should reject mathematical infinity entirely. You can now forget about part 1. Part 2. Okay, now it's going to be a little more technical. Formal number theory is about the natural numbers. Those are the numbers 1, 2, ... And they're the formal axioms of number theory, the piano axioms, PA. They're the algebra axioms you would write down, and they're the induction axioms. I won't specify them. Is all of mathematics just a study of the formal consequences of PA? If so, where does that leave infinity? There's no infinity in the natural numbers. There's potential infinity. Okay, well, if we move a little bit away from number theory and take our first step into that ultimate universe, we get second-order number theory. PA2, 2 is for second order. The objects are the natural numbers together with all sets of natural numbers. You have the algebra axioms. The induction axiom is now explicit. Every non-empty set of numbers has a least element. But then you need axioms to say that you have enough sets of numbers, and those are the comprehension axioms. So we have two fundamental structures of mathematics. The first is the natural numbers with plus and times. The second is that for second-order number theory. Arguably one of the most famous theorems of modern mathematics is Wiles' proof of Fermat's last theorem. Wiles' proof is not even in ZFC, the first published proof, because it used Grothendieck towers. And it's certainly very far from a proof in second-order number theory. So a natural question is, can Wiles' theorem be proved in just piano arithmetic? And this has been widely discussed. And I will make the provocative claim it's not the right question. So I'm going to introduce you to a new theory, finite number theory, FPA, finite piano arithmetic. The objects are the natural numbers starting with 1 and continuing up to some largest number which is otherwise unspecified. You have the algebra axioms, but multiplication and addition now are just relations. They're not operations which act on all numbers because we have a largest number. We're not doing an arithmetic mod n. And then you have the induction axiom, various ways you can state it. Here's one, it's based on the pigeonhole principle. If f is a function on numbers defined by a formal property p, then then that function is one-to-one, takes different numbers to different numbers, is equivalent to saying it's onto. Pigeonhole principle. Okay, every natural number yields a model or universe of FPA. The universe which contains only 1 yields the simplest model. Remember, a model of FPA starts with 1 and goes up to some largest number. That largest number may be 1, or maybe 2, or maybe 3, maybe a googolplex. So you can work in FPA. It's a very restricted setting, but it's an amusing exercise to show that you can define exponentiation as a relation. It's much more subtle than doing that in arithmetic. So Fermat's last theorem is a formal statement of FPA. Can Weyl's proof be proved in FPA? If the answer is yes, then mathematical infinity plays absolutely no role in proof, not even potential infinity. The Riemann hypothesis can also be formulated in FPA. That's one of the most famous open problems in mathematics. In fact, curiously, almost all of the famous open problems of number theory have coincidentally already been refined to problems in FPA. The FPA perspective also generates many new questions. Is all of mathematics just a formal study of FPA? Even the number theorists wouldn't like to hear that. Let me give you a simple example. Euclid's theorem that there are infinitely many prime numbers makes no sense in FPA. But Bertrand's postulate does. There's Bertrand's postulate. It says if you take an integer greater than or equal to 2, there's a prime number between n and 2n. If you look at Erdős's proof of Bertrand's postulate, one could probably show that if in FPA, if 2 to the n exists, then there's a prime number between n and 2n. But that doesn't prove Bertrand's postulate in FPA. What happens if 2n is the largest number? The Erdős proof doesn't even have a chance of working. I think one needs a new proof. Okay, Ramsey's theorem. Suppose n is a natural number, a set x is an n set if it has exactly n elements, and we'll use that notation to indicate all of the n sets x such that x is a subset of y. There's Ramsey's theorem. Take the numbers 1 up to m, color the n sets of those numbers by n colors. You specify how large, I'm sorry, I didn't do the quantifiers. For every n and for every k bigger than n, there is an m, and there's the theorem. It says if you color the n sets from 1 up to m with n colors, you can find a set. It's constant on the n subsets of that set A, and A has at least k many members. So you say how large the clique you want, and if you have enough objects and you color the n sets of those objects with n colors, you can find a clique with exactly that, at least k many members. Sometimes called the party problem. Then there's the infinite Ramsey theorem. Color the n sets of integers with n colors, then you can actually find an infinite set on which that coloring is constant for all the n subsets of that set. Ramsey's theorem is proved in PA, and there's a stronger version which is also proved in FPA. The infinite Ramsey theorem is proved in second-order arithmetic. Okay, now something interesting, the Paris-Harrington theorem. For every natural number n, there is a natural number m, so that if you color the n sets from 1 up to m with n colors, you can find a set, all of whose n subsets are colored the same. The cardinality of that set is bigger than n, otherwise it's trivial, and A has as many members as its least element. Somewhere in between the Ramsey theorem and the infinite Ramsey theorem. And in fact, this easily follows from the infinite Ramsey theorem by a compactness argument. Every infinite set has more members than its least element. The Paris-Harrington theorem says that the theorem cannot be proved from PA unless PA is inconsistent. So kind of what looks like a trivial change on the Ramsey theorem yields a version expressible in arithmetic which cannot be proved in arithmetic. Now you can use the Paris-Harrington theorem to generate some very interesting large numbers. If n is a natural number, pH for Paris-Harrington n is the least natural number m, which witnesses the Paris-Harrington theorem for n. pH 10 is unbelievably large, cannot be written in decimal notation in our universe. And pH 11 is vastly larger than pH 10. And yet they have relatively simple definitions. Now, you can do Gödel sentences in FPA. First of all, you can write down a formula in the language of finite arithmetic which expresses that there exists y such that y is phx and 2 to the 2 to the y exists. And then you can use that to write down a Gödel sentence, theta sub g. This is in the language of FPA. This sentence asserts that there's a proof of my negation of length less than pH 10, that very large number, and pH 100 exists. pH 100 is just beyond. And you express that by saying that the formula phi sub pH of 100 holds. Assume PA, then the negation of theta g is true, and you can write down the proof. There's a proof of the negation of theta g from FPA of length less than pH 11. How can we be sure there's no proof of not theta g from FPA of length less than pH 10? Or maybe even of length less than 10 to the 24th. And you might say, well, who cares? If there were such a proof, maybe of length less than 10 to the 24th, and maybe alpha mind, whenever that comes online, will find it, or you guess and certify it. Mathematics is vacuous. If this Gödel sentence is true, all of mathematics is vacuous. Everything that's ever been done. So how do we know it's not true? Well, we can prove that, that theta g is not true from arithmetic, but that doesn't help. Okay, you now can forget about part 2, and we move on to part 3. And I'm going to have to start talking faster. Well, so we have this dilemma that maybe large finite is contradictory, which would be a very bad thing. So we'd like to argue that can't happen. We'd like to secure the finite. But if we can secure the infinite, clearly we have secured the finite. So the simplest setting for the study of the infinite is second-order number theory, which I've already talked about. We have the axioms. So can we answer the basic questions of second-order number theory using or starting from the piano axioms for second-order number theory, and thereby show that the conception of arbitrary sets of natural numbers makes sense. All right, so we look at the structure of second-order number theory, and we realize it's really the familiar structure of the reals with plus and times, which you all learned about in calculus, together with very simply defined sets of real numbers. These are the projective sets, and not projective in the sense of algebraic geometry. If you view the reals as contained in the power set of the natural numbers, which is a natural thing to do, the projective sets are those sets of real numbers that can be logically defined in the structure for second-order number theory. So now we can take the familiar notions of set theory and localize them to this fragment of the universe of sets. So we can take the axiom of choice and define the projective axiom of choice. And there it is. It's exactly what you would expect if you're familiar with the axiom of choice. I'm not going to read it because I'm going to run out of time. Just taking the axiom of choice, projectifying it. We can do the same thing with the continuum hypothesis and formulate the projective continuum hypothesis. Again, we're localizing the continuum hypothesis to the projective sets. The continuum hypothesis is the assertion that if you have an infinite set of real numbers, you can put it into one-to-one correspondence with the naturals, or you can put it into one-to-one correspondence with all the real numbers. There are no intermediate infinities. So we just do that through the projective lens. By 1925, almost 100 years ago, these two problems were considered hopeless. And in fact, they were hopeless. They're unsolvable, even from the ZFC axioms. And that comes from combining Gödel's work on the constructible universe and Cohen's celebrated proof of the independence of CH. But maybe we can answer these questions by sharpening our conception of second-order number theory. We just don't have all the axioms. Well, let's introduce a projective frame. A projective frame is an extension of the formal axioms. The extension should be specified by a recursive set of formal axioms. This extension should be consistent with the axioms of set theory. We're working in the context of V. And this extension should be immune to Cohen's method. Well, Gödel actually produced the first frame, and I'll call it the Gödel frame. This is the projective frame given by Gödel's axiom V equals L for the universe of sets. The Gödel frame implies both the projective continuum hypothesis and the projective axiom of choice. But there are other frames. The Michowski-Steinhaus axiom of determinacy yields another projective frame. This is the PD frame. The PD frame implies the projective continuum hypothesis, just as did the Gödel frame, and the PD frame implies the projective axiom of choice. But we can formulate the strong projective continuum hypothesis. If X is an infinite set of real numbers and X is not countable, then it contains an uncountable closed set. The strong projective continuum hypothesis implies the projective continuum hypothesis, but they are not equivalent. And then we can talk about the projective well-ordering principle, that there is a well-ordering of the reals which is projective. The projective well-ordering principle implies the projective axiom of choice. The projective well-ordering principle refutes the strong projective continuum hypothesis. So now we have divergent frames. Assume the Gödel frame, then the projective well-ordering principle holds. Assume the PD frame, then the strong projective continuum hypothesis holds, so the projective well-ordering principle does not hold. So Mello's theorem on the equivalence of the axiom of choice and the well-ordering principle does not apply to projective frames. Many, many frames appeared, a bewildering array of projective frames. But in the 20 years or 25 years after Cohen's discovery of forcing, the PD frame remained the only projective frame known in which both the projective axiom of choice holds and the strong projective continuum hypothesis holds. And that led to a natural conjecture that characterizes the PD frame. And then on the basis of that, we might have the one true frame. That turned out not to be true. There are many projective frames in which the strong projective continuum hypothesis holds. The PD frame is false, and the projective axiom of choice holds by a theorem of Steele. It looks like the attempt to understand second-order number theory is just failing completely. So let's take the V perspective. The axiom that there is a measurable cardinal is a fundamental large cardinal axiom. Robotin's theorem from 1964 assumed there is a measurable cardinal, then the Gödel frame is false. Well, that's interesting. The conception of V, the universe of sets, just eliminates the Gödel frame. What about the other frames? There was an unexpected and perfect alignment. There's first the Martin-Steele theorem. If there are infinitely many Woodin cardinals, then the PD frame actually holds. And in fact, it's the one true frame. The PD frame is equivalent to the theory of second-order number theory as given by the ZFC axioms. Together with the axioms, there are n many Woodin cardinals, one for each n. A perfect alignment. New truth of FPA. The PD frame is consistent. And I'll make a prediction. This claim will not have been falsified by the 1000th anniversary of Gödel's matriculation at the University of Vienna. Part 4. I have 3 minutes. I'm going to talk very fast. Yeah, I can forget everything. But have we really secured the infinite? The PD frame is secured by the conception of V, so we enlarge the scope. This demands that we better have a V frame. This should be immune to Cohen's method and be compatible with all large cardinal axioms. Up to about 15 years ago, this seemed completely hopeless. But now we have the ultimate frame. By generalizing the projective sets, we're led to the axiom, a formal axiom, V is ultimate L for the universe of sets. It settles the projective continuum hypothesis. It yields a V frame, immune to Cohen's method. But is it the true axiom, and does it pass the large cardinal test? Well, what about the large cardinal test? Assume V equals L, there are no measurable cardinals. Gödel's axiom fails the large cardinal test. It provides a V frame, but we have to reject it. The ultimate L conjectures are a series of precise mathematical conjectures which, if true, show that the axiom V is ultimate L passes the large cardinal test. These conjectures are statements, well, the ultimate L conjectures also would provide compelling evidence that the axiom V is ultimate L is the true missing axiom for set theory. What about these conjectures? Well, they're statements of number theory. They're not statements about the universe of sets. They must be either true or false. They cannot be meaningless. So if you had access to an oracle for arithmetic truth, you could just ask whether these conjectures are true. All right. Now I will end with, so one of the themes for this meeting originally was, why has the problem of the continuum hypothesis not been solved? I will make a provocative claim. For over 60 years, and this includes the entire modern era of set theory, the attempts to solve the problem of the continuum hypothesis have focused on the question, given that there is a well-ordering of the reals, is the cardinality of the reals omega 1 the first uncountable infinity? This is not the right question. So I will make my provocative claim. The correct question is there a well-ordering of the reals? Because if there isn't a well-ordering of the reals, the continuum hypothesis no longer makes sense. Now, if you answer this question, explain why there's a well-ordering of the reals instead of just assuming it, well, that understanding will lead to an answer to CH. We've been studying the wrong problem. The axiom V is ultimate L explains why there is a well-ordering of the reals, and it implies CH. Thank you. That's it. I almost only went over a little bit.
Thank you very much. I assume there are lots of mathematicians here, and they will perhaps take up your provocative question and spend a few more decades thinking about it, and we'll see what will come from it. Our final lecture today will be given by my colleague, Sandra Müller. I hope she's here. Ah, yeah, perfect. Sandra Müller is an associate professor of mathematics at the TU Wien, so the Technical University of Vienna, and she specializes in set theory with a focus on connecting inner model theory, determinacy, and descriptive set theory. I have to confess, I have no clue what any of these are, or I mean, almost no clue, but I understand that the inner model theory builds directly on Gödel's work, in particular on his notion of the constructible universe. Is it correct? Okay, I'm sure she will explain this to us. Professor Müller currently leads the world's largest research group in inner model theory. And previously, she was a L'Oreal Austria Fellow, as well as an FWF Elise Richter Fellow. In 2022, Professor Müller received the prestigious FWF Start Prize and the prize of the Austrian Mathematical Society in 2022, yeah, same year. And I think that's the highest prize one can actually win in Austria. So quite good, yeah? In the same year, she was also elected to the Young Academy of the Austrian Academy of Sciences. Sandra, we are very much looking forward to your lecture, which is going to sketch out quite ambitiously a scenario for the solution to Gödel's problem of finding good axioms that decide natural mathematical statements. Please go ahead. Thank you.
Well, thank you very much. So, I mean, I have to admit a few words will sound very familiar from Hugh's talk, but as he said that he can forget everything he said after the part, I will have to redefine them again. Okay, I mean, of course, I have to start with Gödel. I mean, it's like the same start as all the other talks, sort of, but I think you cannot say it too many times. So Gödel showed that every reasonable formalization of mathematics automatically results in statements that can neither be proven nor disproven in this formalization. So what does it actually mean? What is a formalization of mathematics? If you're not a mathematician, you can think of this as just a toolbox. A toolbox that we mathematicians use to find out if something is true or false. More precisely, I mean, we collect some obviously true statements that we call axioms, and we have some rules how to obtain new statements from these obviously true ones, and these are going to be true as well. This is how we prove things. So how can it be that there is a statement that can neither be proven nor disproven? Well, Gödel's one has somehow, if you say it informally, a very easy phrasing. You can just say the statement, I am not provable. Well, if you go home and think about it, I mean, it kind of makes sense, you know, that you cannot prove that you're not provable. But this is very theoretical. Yeah, this proves to us that not all questions in mathematics can be answered with proofs. But, I mean, this statement does not have any practical meaning. Right? So what does this actually mean for us? What does it mean for mathematical practice? And is this something we should worry about? I mean, is this something I should worry about? Maybe this is something you should all worry about. So let me give you an example. So let's start with Cantor's continuum hypothesis. So this is Georg Cantor, and more than 100 years ago, he asked a question. This was before Gödel. So he asked, is there a set of size strictly between the size of the natural numbers and the size of the real numbers? So let's just write it down more formally. He made it a hypothesis. He says, well, there is no set of size strictly between these two sets. So what does it mean? The natural numbers are just the numbers that we can count. 0, 1, 2, 3, and so forth. It's an infinite set. Well, we will never stop counting. The real numbers are all the numbers that you can think of. So they include the fractions, pi, yeah, whatever number you want to think of. Yeah, these are the real numbers. But actually, I mean, what does it mean that one, in the sense, infinite set is larger than the other? You know, I mean, of course, the real numbers are more than the natural numbers. I mean, there's the number -1. That's not in the natural numbers. Yeah, so what do we mean by size here? Well, let's step back and just say, okay, when is one set larger than the other? Let's start with an easy example. There are two sets. Which one is larger? Well, I will help you a bit. You know, we can count how many numbers or how many points there are. The orange one has 5. The other one has 3. And 5 is a bigger number than 3. So we solved that problem. The orange one is larger than the blue one. Let's move on. Let's look at a different example. Again, there are two sets. Which one is larger? So let's actually take a test. Yeah? I mean, there's nothing to win, but also nothing to lose. So who thinks the orange one is larger? Please raise your hands. OK, who thinks the blue one is larger? Who thinks they're equal? OK, so, I mean, if we prove things by raising hands, I think we realize this cannot be proven, yeah? But let me help you, yeah? So actually, we don't really need to count how many points there are, right? If we put them in order, you can start connecting them, yeah? We can find one orange one for one blue one, the first line, the second one, the third one, and then we realize, actually, there are 2 points missing, yeah? So it's clear, in this case, that the orange one is larger, again. And we can use this idea to also compare infinite sets. Let's take two infinite sets. Let's take the set of natural numbers, 0, 1, 2, 3, and so forth. And let's take the set of integers. Yeah, so the set of natural numbers, and together with the negative numbers, -1, -2, -3. And let's try to draw arrows between them. So we start with the number 0. Say it goes to 0. Number 1 goes to number 1. Well, we could continue like this, but actually, if we do that, you know, and we keep putting the numbers down here, then we miss all the negative ones. Yeah? I mean, there's nothing above there. But actually, if we do it a bit more clever, we can catch all of the numbers. So we can move the number 2 to -1. Number 3 goes to 2. Number 4 goes to -2. So we keep alternating back and forth. And if we do that, we manage to assign to each orange point a blue one, and the other way around, if you want. So this is what we mean by that the two sets have the same size. Now, if we manage to find errors that map each orange one to exactly one blue point, then the sets have the same size. And similarly, we can say when one set is larger than the other, if we're not able to do that. So let's take this as our definition, yeah, of the set A that has to be of size strictly between the natural and the real numbers. And then it turns out that this statement can neither be proven nor disproven from the standard axioms of mathematics, ZFC. So what do we do with this? You know, as mathematicians, you know, it's not really satisfactory that we cannot prove something. And Gödel already came up with an idea for a solution. And let me say, you know, this was before we actually knew that we couldn't prove it. Yeah? But what Gödel suggested was, well, maybe if we add something to our toolbox, then we can prove it. So can we prove or disprove the continuum hypothesis by enlarging the toolbox and adding new axioms? Actually, there's a specific set of axioms that he suggested, and these are large cardinals. So large cardinal axioms are postulating the existence of large infinities. Let's just draw them in a line. Yeah? Let's try to draw. You know, at the bottom, the smallest infinite number is the natural numbers. And the natural numbers, they're quite peculiar. It's at the smallest infinity, but they're already quite large, if you're a finite number. Like, imagine you're a finite number and you're trying to climb up to the naturals. You are never going to do that, The only operation you have is +1. If you're a finite number and you add 1 and 1 and 1 and 1, you will never reach all the finite numbers. You cannot reach infinity by adding just 1. And now we know, okay, the set of real numbers is even larger. Cantor proved that. But now imagine, maybe we can think of even larger numbers. For example, there's something like an inaccessible cardinal. An inaccessible cardinal, that's the smallest large cardinal notion we know. And it's so large that we cannot only not reach it by +1, it's not accessible by any method in some sense. So we cannot reach it by just taking power sets, or we cannot reach it as a limit in some sense of smaller infinities. It's really inaccessible to us. And I said, that's still a very small large cardinal. The measurable cardinal is even larger, and even larger than that is the Woodin cardinal. I'm not even going to try to define them to you, but just imagine, it's much larger than anything that you could probably imagine to exist. But still, the question remains, do they actually help? So does ZFZ, together with large cardinals, prove or disprove the continuum hypothesis? Let's see. First, what does it actually mean that something is independent? What does it mean that we cannot prove or disprove it? Well, we have our mathematical universe. That's usually called V, and maybe you get an idea why we call it V. It looks somehow like this. You start from the bottom, and then you sort of climb up, and you add all the sets, all the mathematical objects that you can think of, and the ZFZ axioms hold in there. But now we can build different universes. So we have our mathematical universe, and in there, Gödel found a smaller universe in which the continuum hypothesis is true. So it has the ZFZ axioms and also CH. So this is called building canonical models. And on the other hand, there's another method of building universes or building models. And Paul Cohen in the 1960s managed to build a model where we have the ZFZ axioms, but CH is false. He got the Fields Medal for that by developing the forcing method. That you can use the forcing method to build many other nice universes. So ZFZ cannot prove CH or not CH because we have two mathematical universes. In one, CH is true, and in the other one is false. But if we go back to the question Gödel asked, can we decide CH with large cardinals? Well, the problem is that large cardinals are quite immune to this forcing method. So actually, we can also build two universes. One with DFZ, large cardinals, and CH, the continuum hypothesis. And we can build another one with ZFZ, large cardinals, and not CH. So this seems like they're not helping at all. As a teaser, they do help, but I will get back to that in 10 minutes. But if you just try to prove it directly, it seems like there's nothing you can do about this question. But let's go a little bit deeper into Gödel's work on constructing the constructible universe. So what is this model where the continuum hypothesis is true? So Gödel came up with the idea to consider canonical models that are constructed bottom-up. And he proved that there's this canonical model in which CH holds, and the model looks like this. It somehow has a similar shape as the universe, but it's thinner. So we start from the easiest set we have. We start from the empty set. There's nothing. And then we build a hierarchy. And at each successive step, we take everything that's definable from the previous level. So instead of just taking all the sets, we only take the ones that you can somehow control. And we keep doing that. And this is a construction throughout the infinite. So at some levels, we take unions. And actually, the first time we do this, all sets are still finite. We start from something finite. But if we do this really, really long, we get a rather large universe. This universe is as high as the mathematical universe V that we started from. It's just thinner. So the question remains, I mean, now we have a canonical universe. It's actually a model of the continuum hypothesis. But can this canonical universe have large cardinals? Well, the quick answer is no. Unfortunately not, at least not the powerful ones, as measurable cardinals or Woodin cardinals. They do not exist in Gödel's universe. Okay, so that was too narrow. But maybe we can just tweak it a little bit. So can we build models that have the same properties as Gödel's universe L, but they possess large cardinals? And the answer to that question is yes. I mean, this is the research area of inner model theory. Yeah? It started from that question, at least up to some level. Yeah? I mean, we're climbing up the large cardinal hierarchy and try to build canonical models for larger and larger infinities. And these canonical models are actually called mice. So in case you see a mouse in inner model theory, this is what they mean. But we are left with the ultimate question. Now we are sort of enlarging the canonical models. But if we are asking about truth, we have to ask about V. We have to ask about our mathematical universe. Is this a canonical model? What does this mean? Yeah, well, there's a formulation that is due to Woodin. So it's the axiom V is equal to ultimate L. So let me read it, and let me try to explain a little bit. So what it says, okay, first of all, there are a lot of large cardinals, a proper class of Woodin cardinals. And then for each sigma 2 sentence phi, and here, so a sigma 2 sentence is something of the form, there is a level such that at this level something holds. And so for each such sentence, there is a universally bare set, which is a very nice set of reals that has a super property. We can extend it canonically. So it's like a very uniform, very nice set, such that if we look at a model that's given to us by the universally bare sets, so it's called the hereditarily ordinal definable sets in L of AR. So we build a nice model, and in this model, the sigma 2 sentence phi holds. So, I mean, roughly in words, this means that for each sigma 2 sentence, which is true in V, there's a canonical model in which it holds. It's a reflection property. If we have something that's true globally, we find a canonical model where it holds. That's very roughly, the idea between the question whether V is a canonical universe. Is this the axiom that Gödel was looking for? So remember, we ask if we can prove or disprove the continuum hypothesis by enlarging the toolbox, by adding new axioms. So maybe this is one we can add. Well, at least this naturally implies the continuum hypothesis. It naturally gives a well order of the reals, and it satisfies CH. So just as an idea, I mean, both CH and not CH can actually be written as sigma 2 sentences in this way. I mean, that's roughly the relation. And recent advances in set theory make this axiom more elegant and natural. But let's first talk again about large cardinals and the continuum hypothesis. So was Gödel right? I mean, is there a connection between large cardinals and CH? Can we actually say something? Well, we can if we ask about fragments of the continuum hypothesis, actually. So Cantor already, that was the guy who asked the question, he already proved that there are no very simple counterexamples to the continuum hypothesis. So if you want to find a set of size strictly between the natural numbers and the real numbers, it has to be somehow complex. It cannot be closed. And if you assume large cardinals, it can also not be constructible in the following sense. So large cardinals imply that there are no constructible counterexamples, no counterexamples in L of R. Everything constructible from the reals. And we can go even a little bit beyond. So in addition, the theory is frozen. So this means that we cannot add new counterexamples by the forcing method. The forcing method is our machinery to produce counterexamples to CH. If you assume large cardinals, I mean, CH holds sort of in L of R. I mean, there are no counterexamples from L of R, and there are also no counterexamples in L of R that we can introduce by forcing. And if we are willing to assume even more from something called ceiling, there are no counterexamples in an even larger, smaller universe. So in everything defined or constructible from the universally bare sets and the reals. And again, the theory is frozen, so no counterexamples can be introduced by forcing. So does ceiling hold? Yeah. Can we actually prove ceiling from large cardinals? If large cardinals would imply ceiling, then they do have a very huge impact on the continuum hypothesis. Yeah, so again, was Gödel right? Do large cardinals imply ceiling? Well, I mean, there's something we can say. I mean, Woodin proved in 2004, assuming large cardinals, ceiling holds at least an extension of the universe. Yeah, they don't directly imply ceiling, but if we collapse, if we take a really large cardinal and we smash it, we make it very small, then afterwards, ceiling does hold. And myself, together with Grigor Sargsyan, recently showed that we can extend this, and we can even get a version of ceiling, not only for sets of reals, but for sets of reals. Yeah, so we can do it for larger universes, in some sense. But how is ceiling compared to V is equal to ultimate L? So there's a positive correlation. First, I mean, if ceiling holds, then there's a natural strengthening of V is equal to ultimate L. Well, I mean, natural for logicians of a set theorists. So this was also suggested by Woodin. It looks very similar to what I had before. Yeah? I mean, we again have that there's a proper class of Woodin cardinals. And now we say for each sigma 2 sentence phi, if phi holds in V, then it holds in heart of L of the UB sets and the reals. You know, there's a there's an easy to miss but very important sort of change of quantifiers here. Yeah? I mean, before we said for each sentence there is a model, and now we say there is a canonical model such that for each sigma 2 sentence, if it's true in V, it's true in this model. So this guy here, this heart of L of the UB sets, is a very canonical model. But it only makes sense to talk about this if we have something like ceiling. So this makes V is equal to ultimate L a canonical axiom. But on the other hand, there's also sort of some bad news. Ceiling prevents us from building mice the way we know how to build them. So they don't look like this anymore. Yeah? I don't know how they will look like. But we know that if ceiling holds, the canonical models that we can construct have to be very complicated. They have to look different. Yeah? So which axiom is true? Well, for me, this is the real question behind the continuum hypothesis that we should answer. Yeah? The continuum hypothesis is a very local question. It just asks about the natural numbers and the real numbers. These questions, ceiling or ultimate L, they ask about the global structure of the universe. If we can answer them, I mean, of course, we get an answer for the small part, but we get answers to many, many more questions that we can ask about the mathematical universe. So we started our journey from the boundaries of mathematics. Yeah? We started with Gödel to the study of large infinities. And the most important thing to remember is that not every statement in mathematics can be proven or disproven. But what do we do about it? Yeah? I mean, I cannot go home and just be satisfied with the fact that we cannot prove something. Yeah? When I learned about this, I had to do logic. You know, when somebody showed me this result of Gödel, it's like, what? I mean, this is not okay. You know, there's something we have to do about it. And what we can do is we can extend our toolbox by axioms, for example, of large infinities. And this gives a clearer picture of our mathematical universe. This does help us answering questions. But it also leaves us with the question, what is mathematical truth? Is something true if we can prove it from large cardinals? Is it true if we can prove it from ZFZ? Do we actually need to prove it? And even more broadly, can this question even be answered by mathematicians? Is this a question for us, for you? Can it be answered by philosophers? Can it be answered at all? Well, I will leave you with that question. Thank you very much.